Welcome to STEAM Powered, where I have conversations with women in STEAM to learn a little bit about what they do and who they are. I'm your host, Michelle Ong. My guest today is Dr. Heloise Stevance. Heloise is a computational astrophysicist who studies stellar evolution and how massive stars live and die, specifically the ones that die as Kilonovae. Join us as we talk about the life cycles of stars, Kilonovae, and roller derby. Welcome, Heloise. Thank you for joining me on STEAM Powered. I'm so happy to have you on here.
Hi, thank you so much for inviting me.
That's fantastic. So we'll get straight into it. You started off in physics and astronomy. So what drew you to that field?
Right, so I was always interested in space when I was a kid, and not like stargazing and looking at constellations. I never had a telescope, but understanding how the world works, especially stars, black holes, galaxies, because these things are so vast and the numbers are just so extreme and incredible that they always blew my mind. And I didn't realize that it was a career until quite late. I don't really remember when, like, at what age I realized that's something I could get into, like, properly as a career. But it wasn't like it was towards the end of my teenage years properly, because none of my family are academics in any shape or form. That is not a thing. Like, we had some higher education, but not like, no.
Yeah.
But I realized when I was looking at unis and where I could go, what kind of courses I could do, that astronomy was a course I could pick. And I was like, oh my God, that's kind of crazy. How that? Should I do this?
Yeah.
And I nearly didn't do it actually,
Oh,
because astronomy is physics. It's a sub subject of physics. And I had marks that were a little bit, like, they were fine, but like I had better marks in chemistry and stuff like that, which is a
yeah.
simple way to pick a degree. Like, do not do that ever. Like, don't pick
Yes.
the best mark. Like, stupid. So I nearly didn't do it, but thankfully I did, and I'm still here today. So here we are.
That's amazing. So did you feel that, because your physics wasn't as strong, did you find that more challenging, or was that just, complete red herring for you? Like it just wasn't really a factor?
It was completely red herring. Like, because it was a marginal difference of like 1 mark out of 20 or
Oh,
something.
wow. Okay.
Like,
Yeah. Tiny.
it was being in my head. Like, it was silly. Um, and no, no, no. Physics was fine. I was okay at all the science subjects. Like, they're just tougher in general, because you can sort of hand wave your way through literature. You can't really through derivations. Not really.
Yeah, it's a little bit more precise.
But no, it was fine.
When you decided you want to do astronomy, like where did you see that course taking you? What sort of, career and work did you think it was going to, lead to?
So by the time I was looking at uni, I was aware that PhDs were a thing. I know that. I don't know when I realized PhDs were a thing. That's such a weird thing. Like, I can't remember what I was thinking 10 years ago. But I knew they were a thing. Because how I picked my university. Um, I picked my university for my undergrad because they had a program in fourth year, so the master's year in England, that selected one or two candidates, so some of the best in the year, to go to La Palma in the Canary Islands to work for an observatory. And I remember
Wow,
thinking, this sounds like a
that's
ticket
a goal.
to PhD. Like, that sounds like a ticket to, like something that helps you stand out if you're going to seek a career in astronomy. And that's why
Yeah.
I picked that university. And then 4 years later, I ended up in that program. So that was kind of the idea. Then after that, kind of like, there's not much point planning for 7 years ahead anyway.
Yeah, no,
uh,
exactly.
but yeah.
So that's brilliant. So what did you do at the observatory?
Well, I observed. So I was what's called a support astronomer. So when you are just some astronomer that needs data, you can sometimes go to the telescope. Sometimes it's not necessary. Sometimes it's just impossible. So if you do programs that are really time sensitive, for example, you're observing a supernova that might happen, you don't know when. It happens one day and then you need to observe. You can't plan those observations. You can't book plane tickets. You can't do anything like that. So those are things you just kind of send an email. You've organized things with the observatory before sending email, blah, blah. But if it's something like a star that just is going to stay there, or a galaxy or whatever, you might go to the observatory to take the data yourself. That being said, not every astronomer is expert in how every telescope works and every instrument on the telescope. So you need people that will help the astronomers navigate how the telescope works. In some observatories or some bigger telescopes, you have a telescope operator who moves the telescope around, and a support astronomer, an instrument specialist, who will also help the astronomer acquire the data. So as it goes through the instrument, what kind of settings you need, make sure that everything works. If there's an issue, help along with that. At the observatory where I was at, the telescopes, the specific telescope was called the Isaac Newton telescope, like the scientist. And it's a very ancient thing. They don't have that much money, so there's only one support astronomer. You're there for the first half a night. You show the telescope around to the astronomers. You're like, so this is how you start the telescope. This is how you move it around. These are the steps you have to follow. If stuff goes wrong, here is how you turn it off and on again. Which is literally what we did. Like, all of the different things you can turn off and on again, do it at the appropriate time, and usually it fixes things.
Yeah.
And you're there for the first half a night with them to help them walk them through it. Then you go to bed at the residencia, but you're still on call for that rest of the night. If they need help, they'll call you up. You can drive back to the mountain, because the rest is, doesn't matter. And then you just go back down the mountain the next day, and they continue with their observations, whatever, 3 days, a week, 2 weeks that they have. Usually no more than, like, more than a week is pretty rare, but yeah.
Wow.
And then you go back for the next round of observers who needs more help to figure it out.
That's so cool. So how long did you do that for?
About a year. Yeah, so that was my master's year. So I was still a student of the University of Sheffield, where I did my undergrad, and also my PhD, actually. So I was still doing a project with them, just some data reduction, smallish. I mean, it took the whole year, like, compared to a PhD or a postdoc, a project that I did on top of being a support astronomer. But a component of my mark was knowing how the telescope works, and helping, doing my job with that. So
That is so awesome. That's brilliant. So after that, yeah, obviously not a problem to get into the PhD program.
it wasn't too bad. No,
No?
oh no, the people at the university I was like, hey, come back.
Come back.
Yeah, so I did. I stayed in Sheffield, actually.
That's great. So what did you focus on for your PhD?
Right, so I did something completely different for my PhD. So during my master's, I worked on near-Earth asteroid. That's what my project was about, looking at how they evolve, their rotation period, that kind of stuff. And for my PhD, I worked on supernovae and what kind of shapes they have in 3 dimensions, trying to understand that better, because it's kind of, it's not just kind of, it's very difficult to obtain 3-dimensional information on something that is just a dot in the sky, literally.
Yes.
When you observe these things as they appear, it's one dot. So it's not like you go from basically 0 dimensions to 3 dimensions, and doing that requires specific techniques. It's something called spectropolarimetry, which I'm not going to go into details because the name is like, there are way too many syllables in this word. This is not okay. And so yeah, you can get 3-dimensional information from that stuff, but it takes a while. And so I reviewed new data. I also, by the end of my PhD, reanalyzed data that was taken 25 years prior in 1993, because the field has evolved so much since then.
Yeah.
That with the knowledge of the field that I'd acquired in my PhD, you can really look at this with a brand new eye and get so much more information out of this data. And what's really interesting is that 25-year-old data, I still haven't analyzed it to its full potential. I
Yeah.
know I have not. There are features in there that we do not fully understand because we don't have the models yet. And I find that super exciting. That is like, I looked at this 25 years later and I found so much more. And I know for a fact that there is so much more to come.
Even though, all this information is old, you're just going to be able to keep learning from it as time goes
Mhm.
on. Like the next generation of astronomers are going to be able to do the same thing and
Exactly.
find more stuff.
Exactly.
That's cool.
The field is still evolving.
That's brilliant. So what sort of things can you learn from understanding the shape of a supernova?
So at first, and that's kind of the point of that 25-year-old analysis, and that's why they stopped there. People were just wondering, are they spherical? Because that tells you about the shape of the explosion, which can tell you about the mechanism, which was not fully understood yet. And so when they started getting those data, they were like, oh my God, it's not spherical at all. We kind of stopped there. They were like, oh, it's not a sphere. Brilliant paper. Um,
Carry on.
just go to bed, drink some water. We're done, guys. Um,
Yep.
so there's loads of other things you can figure out. You can figure out about the location of different elements and how clumpy the ejector is. So there is some degeneracy in the. That's why it's so difficult to do without models. And that's why the analyses are limited when you're just kind of analyzing these things by hand, is
Yeah.
because you can see the ejector is not homogeneous, and there's different things happening at different depths within the ejector. So like if you imagine the explosion in concentric circles or like ellipses,
Yeah.
because it's not a circle, there's different things happening at different depths. So you'll have areas that show more features of calcium or oxygen, and you can try and reproduce that in models to see if you can get the same features, the same levels of clumpiness, the same levels of inhomogeneity. There is one really interesting thing I found in one of the objects where we saw big clumps of calcium and oxygen that had come from the core, um,
Yeah.
that were very far out in the explosion, and it could be a sign that there was a jet that helped power this supernova, because the ejector was oblong, so it had that
Yeah.
kind of elongated shape, which can be for a number of reasons, but that kind of supernova is associated with jets, so it's like, well, maybe there could be something like that. But also what you know is that if there is a jet in those directions, then it will entrain some of the material from deep inside the core of the star to the outside.
Yeah.
And we kind of saw that, which is pretty awesome. But you can't be 100% sure unless you have numerical models that give
Yeah.
proper things. So I'd love to see that kind of stuff being done by colleagues in the future. But that was pretty exciting because it's like,
That is very cool.
so.
And yeah, because like even you think about terrestrial explosions. I mean, you've got all the different layers of the different reactions that occur inside, but it also depends on the composition. So you're able. Can you tell what the star is composed of when it's supernovas?
Mm-hmm. Absolutely. So that's the spectroscopy aspect of things. So with spectroscopy, you can tell different features, like different colors of light are brighter because of different elements. Now it's a mixture of whether the element actually is here and whether the conditions to make that thing shine is also here. So there's
Yeah.
a combination of the two. But then with the presence of these features, with the polarimetry, you can tell whereabouts it is on the sky. So if you picture the 2D like sky, you can tell whereabouts it is in the 2D
Yeah.
space. And with something called the Doppler shift, so whether light is bluer or redder than you expect, you can tell at what depth it is, and that's how you can retrieve this three-dimensional information, because the polarimetry gives you information on the plane of the sky, so in 2D, and then with things we know how to do with spectroscopy, you can get that notion of depth, and that's really awesome.
That is very awesome. So, is that what you've written your code for?
That's well, I wrote some code for that, but that's not the main stuff that I do anymore. Actually, I did that for my thesis,
Ooh.
but I moved out of that field. Well, I keep saying that. So I'm not active in the field anymore. I still talk about some of the work that I did in my thesis. I'm giving a talk on it next week, and stuff. So I still try to advertise some of the work that was done, but I am not an active collaborator of anything because I'm busy with other things at the moment.
That's very cool. So, what are those other things?
Right, so I work in stellar evolution now. So that kind of it's a slightly different field, but it does bring back to your like boil down to supernovae again if you wanted to.
Yeah.
Because I figure out how massive stars live and die, and many of them die as supernovae. So the main
Yes.
point of what I do is figuring out how they die as kilonovae, which is a different type of explosion that happens when two neutron stars merge together and then they explode. And in the process, they also create gravitational waves as they are
Yeah.
approaching, as they are spiraling in. And these gravitational waves can be detected, which is the exciting thing because that's the new field. You know, gravitational waves. We saw the first ones in 2015. It's all new.
Yeah.
We've only seen so far one detection of a neutron star merger with the gravitational waves and with the explosion. And if we can have all of this information from the waves, from the light of the explosion, we can tell a lot about the system itself that exploded. And then people like me and my boss and our teams can try and figure out what stars came before that. We try to rewind the clock
Wow.
with stellar models, because these stellar models take stars from their birth and then evolve them through time and tell you what they're going to look like every step of the way. And so what you can do after that is go and compare the observations of your observational friends telescope and took a pictures, and you compare the
Yeah.
models and you see what matches and what doesn't match, and this way you can figure out a star's past and a star's future.
That is brilliant. So, because, the life cycle of a star is, it could be millennia, it's a very long time scale.
It's crazy. It's between 3 million years and trillions of years, longer than the current age
Yeah.
of the universe. Yeah.
So, how do you, because of how long we've been doing this sort of stuff, or rather, you guys have been doing this sort of stuff, like the amount of time that we have had to collect this kind of information is just kind of like this tiny
Yeah.
little thing compared to like the entire life scale. So, how do you extrapolate that much information?
That's such a good question. I get that question all the time. So one of the hardest thing in astronomy is that you're basically stuck with one picture in time, and you can't repeat the experiment in the lab because the conditions of space are so extreme they cannot exist on Earth for most things. And so computers are the answer to that. Now, fortunately, space is a fantastic lab that has many different regions that create many different conditions, and we can observe those. So there are clusters that are very young. There are what we call stellar nurseries, or H2 regions for the people in the know. There are in the galaxy and in nearby galaxy where we can observe very young stellar populations. We can look at their characteristics and see how well it matches with our models. We can look at more distant galaxies that have much older stellar populations, see what characteristics they have, see how well it matches with our older stellar populations. And so, although we don't have the movie of how one galaxy has evolved, like over time from the birth of the universe until now, we can sort of put that puzzle together using different galaxies that cover a range of ages and compositions and sizes and etc etc. So that's how we kind of try and put that back together.
Oh, that's brilliant. Yeah, so just taking all the snapshots and just sort of getting the comparisons. Yeah.
Exactly. You take all of the different pictures that the universe is giving you and you try and build a coherent one with the help of physics as well. You know, it's not just It's not guesswork.
Yeah, yeah.
Well, I'm trying to put physics in that too. Uh, and the good thing with computers getting this good is that the better the computers get, the more physics you can put in, because physics is computationally quite intensive. If you're going to, the more things you try and take into account, um, the more calculations you need to do. Um, we have loads of different teams that have different simulations at different scales, because you can't, at the moment, you can't have one simulation that covers everything,
Everything.
from the
No.
minute, nuclear synthesis in the core of stars to how a star shines and what it's going to look like, to how it interacts with its companion, to how that system interacts with nearby system, to how this cluster interacts with other clusters, to how that forms a galaxy, to how that scales are insane. Like, I cannot emphasize this.
Yeah.
The scales are insane. So not only do you need multiple snapshots from the universe to compare to your simulations, but you need multiple like snapshot simulations that work on different scales in order for you to be able to build that big picture.
Yeah, because you can't get a better idea just from a single model. You need to be able to see all the possibilities of all the different models that could possibly be created.
Yeah, I mean, there's just so many different fields that you need something that will work for that field, that is
Yeah,
relevant to
definitely.
that scale.
Yeah, and then you end up being very super focused on one very particular area like yourself.
Yeah, that's interesting because I'm not actually that focused. I mean, obviously, compared to a lay person, I am. But I'm kind of the ugly little duckling of astronomy, because I'm like, I did near Earth, like, I did novae in my undergrad, then I did near Earth asteroids in my master's, then I did supernovae in my PhD. Now I'm doing stellar evolution and another kind of explosion. I'm all over the place, like,
Yeah.
precision is my second name. I know people who've been doing the same stuff for like a decade and a half. My husband still uses some of the codes that his supervisor gave him during his
Oh,
PhD,
wow.
because he's been doing the same sort of stuff and an extension of that stuff, which is great. Like, I'm kind of envious of those people, because it's like, oh my god, you are the expert in that thing. Whereas I'm like, well, we'll see what happens next month, I guess.
Yeah, but that's still very cool because all the stuff that you do, even though it is covering a wide range within that field, it still informs each other. It still carries one to the other, and there's a lot of stuff that does interrelate.
Yeah, I hope I can bridge the gap between different fields, because I have this kind of wide view rather than um, being stuck in one niche. So,
Yeah, that's very neat. So, you mentioned that, there's only been one observation for Kilonova, but how, okay, because a lot of stuff is being collected by all the telescopes, so you have a ton of data, and I'm guessing, like, did they just see this thing and went, this is like a supernova, but not? How did they realize there was a thing?
that's such a good question. Oh, I love the discovery of the Kilonova is one of the best story I'll ever tell. I was on the outskirts of the field, so I'm not on any of the papers, but I knew the people that worked on that stuff. So people knew that Kilonova were going to be a thing. Like, there were still debates about what it was going to be called, but it had already been in the literature. People had thought about what a neutron star merger could be. People already thought that they were the cause of what we call short gamma ray burst. There's another kind of gamma ray burst that's long, which is why we have the short in front. But just nobody was sure until you could actually see it. And so what happened is that LIGO, which the people that observed the gravitational waves were doing their thing, and they saw a neutron star merger. And they can tell from the gravitational waves, because the signature is very different from a black hole merger, because the objects are much smaller. They don't have the same mass
Yeah.
at all. And so they can tell exactly what kind of mass the objects have. And they were like, this is neutron star stuff. This is... And they can also tell you roughly what distance it's at, and they were like, this is nearby, this is really close, this is good, guys. And so once that news came out, I mean, it was kind of, they kept a lid on it, but a third of the astronomers, of all of the astronomers, knew about what was going on. uh, like
Best kept secret. The
was
worst.
like, so basically all of the things they had put in place, because people had thought about that possibility and they had follow-up strategies. So what you do in that
Mm-hmm.
sort of case, when you think, okay, we might be able to observe this this sort of cool stuff, you can put in you could put in requests at the telescopes ahead of time saying, if this stuff happens, then we will need this sort of time. Or in that case, it can be so exceptional that the people that direct the telescopes are like, we will just take control of the telescopes for a little while. Sorry for the people that are already here. My husband was observing at the VLT at the time, and so they took
Nice.
2 hours from him every night at the beginning of his night to observe the object. And so basically all of the telescopes that could look at it looked at it, and all the wavelengths that they could. Now, very quickly, they found they had found the counterpart, so the light from the object, and they managed to find it because they didn't just get the gravitational wave, they also got the gamma ray burst. And that's very cool because that allows you to it helped them triangulate the origin of the signal. And so they had a bunch of small telescope that can move really quickly, like look at all of the galaxies of the sky, like, oh my god, where is it, and they found it. And and when they found it, all of the big telescopes that are big and clunky or whatever, that need someone special to be like, hey, we're going to take 2 hours of your time, then do that in the following days. And so
Nice.
obviously it was a secret, but then because everyone was like, people were like, well, where is my telescope time going? Like, looking at the logs of the telescope to be like, well, they're looking at this position exactly. So everyone knew.
There must be something going on here. We need to have a look too.
Everyone knew kind of where the object was. Like, it was so secret. Like, they weren't allowed to be in the control room of the telescope in case someone saw the spectrum coming, and like they didn't want to get spooked and everything. So it was the worst kept secret in astronomy, also because one of my mates, he's one of the biggest theorists of the late second half of the 20th century. He writes books about supernovae and stuff. He tweeted about it, bless him. He was like, oh my god, electromagnetic counterpart to neutron star merger, blow your socks off, on Twitter without anyone before any official announcements. So he got reprimanded a little bit. Everyone, okay. So everyone knew, and eventually, the papers came out, and it was great. But yeah, it was definitely the worst kept secret in astronomy, and that's why it makes me laugh when people are like, "Oh my god, there is alien life, and they're just hiding it from us." It's like, if astronomers know something exciting,
we can't keep a secret.
Like, this is always there's no way.
There's no way they could possibly keep this from anybody else. That's brilliant. And it's funny because you're keeping a secret from a bunch of people whose sole job is to extrapolate information from the little that they've got.
Exactly. It's like, that's not going to happen. They just want to keep it a secret enough that nobody publishes a paper, they don't want to get
Yeah.
Which you understand, because they've put a lot of time and effort into that.
Exactly.
Yeah, it was very funny.
That is great. That's such a brilliant story. So, with all of these observations, because you can book time in, that suggests that all of these events don't happen so quickly that you can't have a little bit of time to prepare. So how long did it take for the Kilonova event to occur?
So the gravitational wave happened, the short gamma ray burst occurred 1.74 seconds later. So the telescope was already observing, and the timestamp was one of the smoking guns that the two were connected. That was very important.
Yeah.
But then the kilonova starts fading in a few days, and so you have to be extremely fast. So once they had a triangulation between the gravitational wave and the gamma ray burst, in the next day, they I can't remember if it's in the next day or the next 48 hours that they found the counterpart. I'll have to look that up. But they found it really quickly because they managed to catch the final rise of it.
Yeah.
Bands, which only happens in 5 days. So they did a fantastic job, and you have to, if you're going to get good data on these objects, because supernovae happen on a time scale. Like it takes a few weeks for them to fade out of. I mean, obviously, it depends on how bright they are to begin with. Um, but if you can catch a good rise and they fade away, it within a month and a half they're gone. The
Yeah.
Kilonova rise on the time scale of like 5 days, a week instead of 3 weeks. So you're
Wow.
happening three times as fast, roughly.
That's pretty cool. So, given the vastness of space and the number of potential events that could be occurring that are worth looking at, how do you even begin to know how to focus your attentions to know to expect all of these things or to know where to look for? It's just chance.
A little bit, yes. So there is a big thing with chance, especially because we don't know the rates exactly because we've not seen that many. So we expected to see many more neutron star mergers with further gravitational wave observations. We haven't seen that many, which is quite interesting.
Yeah.
Um, Maybe it's just something about the universe. Maybe it's just something about the detectors. We'll get more gravitational wave detectors online in the next few years because now this technology is really up to par. So we're going to get much more in the future, but you can't really know. Um,
Yeah.
and then, but you have to be prepared the whole time. So I'm part of a collaboration called Engrave, which when the gravitational wave collaborations are in observing mode, so they have observing seasons or like observing runs, which last about a year. So the last one ended in 2020, like about a year ago, basically. Um, and when those are happening, we have on-call teams which rotate every week. So there's a few people whose job it is to keep track of the alerts. So the gravitational wave people will do very quick data reductions and send out alerts saying we saw this. It's probably this kind of masses, this kind of observations, and occasionally you get a neutron star merger candidate. Now, Engrave's job is not to find the counterpart; it's to follow up the counterpart when it is found. So for the finding the counterpart, I've got a friend who works with GOTO, which is a telescope on La Palma, whose job it is to slew to the position of the sky that it could be in, because the gravitational wave people give us basically a banana on the sky, a little a
Yeah.
map of probability that like in this potato region,
General area.
the most likely area. So because we don't have that many gravitational wave detectors online yet, the regions are pretty vast, and it can be difficult to explore all of that. Um, but in the future, when we see more neutron star mergers that actually have counterparts, so that makes sense to actually observe, and when we have more gravitational wave detectors online, which will help us triangulate and narrow down these regions, then it will be much more convenient to do these searches. So the way it will work is the telescope will be able to automatically know the alerts and prioritize their observing programs. So they have schedulers that, it's people who think about how the schedulers work, but then they can work automatically, and they can then rapidly slew to the right position in the sky and take a few images and do a little bit of data reduction themselves and tell you this position, like this picture does not look like the picture we took 3 days ago. There is something bright was not there before, and that's the way
Yeah.
you can find these transients. And there's like surveys that do that on the regular, that just scan the sky and they tell you, well, there's a supernova here, 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 and here, and you can have hundreds every day, hundreds of new transients,
Wow.
like things in the galaxy. Either it's variable stars, it can be just simple novae, which would be in the galaxy, supernovae from other galaxies, stuff like that. You can get so many a day if you
That's
just scan the
amazing.
sky very regularly.
That's very, very cool. Yeah, I was going to ask, like, how many supernovae exist, or how do you know how many actually occur at any one time? But that is a lot, but I guess scale, right?
It's not hundreds of supernovae a day, but it's not. It's quite a few. I think there were like
Yeah.
20. I think in 2018 or 2019, I looked at a database and they had 25,000 alerts in that,
Wow,
something like
that
that.
is
So
amazing.
I haven't, like, because I'm not really an observer anymore and I
Yeah.
don't keep track of those, like, I could run those numbers again, but it's quite a lot because they're visible
That's
from a
heaps.
very long distance.
Yeah, that is very, very cool. So, what have we learned from that Kilonova data so far?
So much. First of all, the short gamma ray burst coming from neutron star mergers is a go. That
Yeah,
works. So that's pretty exciting. Oh, God, I should have revised.
I'm
um,
sorry.
it's fine. So because there is just so much that people are doing that is not even on my radar. People have been looking
Yeah,
at what's called the equation of state of neutron stars using these data. The upper mass limit of neutron stars as well, which is still kind of up in the air. We don't really know. It's somewhere in between like 2 and 3 solar masses. But we're not quite sure there. And so some people use that data to place limits, which is very helpful. Some people had a look at the environment of the kilonova. I'm actually going to do a reanalysis of that using our own models, which are binary star evolutionary models, which kind of makes sense because it's from a binary star. So it'd be cool to um, and yes, looking at what kind of environment it's in, how old the population is, all of that stuff. And it seems that there's kind of a younger population as well as an old population, but there's more to come on that in the future. Um, and yeah, this just the day it was published, there were 80 papers on that object
wow.
because all of the papers were held back, were embargoed until the release,
Yeah,
until the press release, and like it flooded our all like news outlets, like because we've got
yep,
something called the archive with new publications every day, and like that they've
yeah,
everything.
smashed.
It was crazy and pretty. It was pretty cool, but yeah, I haven't read like even a small percentage of all
I
of it.
know.
It's just so much.
Yeah, there's just so much information that can be covered. So, specifically with what you're doing, so you're researching about the life cycle and what can we get from all of that?
Right. So the what's really interesting about gravitational waves is the kind of regimes that it probes. We get information from some of the most massive black holes that we've ever seen. Sorry, most massive stellar black holes. Obviously, there's different kinds of black holes. There's the black holes that like are the like dead corpse of stars, and they're tens, few hundred, like 100 solar masses, something like that. And then there's supermassive black holes that are millions or billions of times the mass of the sun. These are in the middle of galaxies. This is not what I'm talking about here.
Yeah,
Um, but that's really interesting to see what kind of population of basically dead stars we have, because we have to be able to reproduce those. We have to be able to make those somehow with our stellar models, if our stellar models are right, you know, we
yeah,
have to be able to make those. But it can also tell us about how stars interacted, like in um, sort of multiple systems. So there are stars, black holes that have been found with gravitational waves. One in particular recently that was published. I think it was discovered in 2019. That was way too massive. It could not have been made by a star. It came from two black holes, 85 or 80 solar mass and 60 solar mass. Like I'm giving around, it's around
yeah.
those masses. I can't remember.
Ballpark.
5 ballpark, 60 and 80 around that. Um, uh, you can't make those with stars as we understand it. You can't make a 60 solar mass black hole. You can't make an 80 solar mass black hole. You can make things that are lighter and things that are heavier, but you can't make this range of black holes. And the reason for that is that a star that would normally make that sort of mass of a remnant kind of goes through a weird process called peri-instability, which is a weird phase of matter where the core of the star is super hot, but also not very dense compared to what it should normally be. And photons split apart in positron and electron pairs. And the reason that's a problem is because photons is the only thing that is keeping that star from collapsing. And
Yeah.
when that happens, nuclear fusion starts again, but in a runaway manner. It just keeps going faster and faster and faster and faster until the whole star is disrupted. And that means that there is nothing left behind. And so all of that mass that could, like, if it wasn't for that process that would normally go into making a black hole of that mass, is instead completely disrupted and spread out into space. And so there is what we call the upper mass gap. There's a lower mass gap as well. Maybe not. People think not. It's complicated. There is probably definitely an upper mass gap.
Probably, definitely.
Definitely. Where we can't make those. And so either there is something we don't understand with how stars that massive evolve and die, or it's because these black holes were not formed by stars. They were formed in a merger. So there were mergers before the final merger that gave us the gravitational wave, which would be possible if you have what we call a hierarchical system. So you have two stars that orbit each other. There's a hierarchy in the multiplicity. It's not like four stars that orbit each other in a chaotic manner. You have like two stars in the middle, and then you've got another another system, binary system, and they kind of orbit each other like that. And so you can have like two stars, like two black holes merging, and then two black holes merging, and then those two merging.
Ah.
That's how you could get your thing. But that's very like brand new field. Need to do simulations to understand how easily that happens, if that's like how possible that is on those timescales. Because obviously it's easy to say, well, two things merge and then two things merge after that, but this stuff needs to happen on a time scale that is short enough that it will happen within the current lifetime of the universe. And that's pretty difficult. You need to have a star that goes through its entire lifetime, which isn't too bad for black holes, because these are going to last 3 million years, 5 million years max, something like that. So pretty fast. But then they need to spiral into each other, and that takes a long time. So there's a lot of stuff that is still unknown, but that is just so exciting, because
It is.
we're just asking more questions than we're answering. Which is
it's just so much speculation. That's amazing.
I love it.
That's very, very cool. So because you're able to get these snapshots of star lifetimes, I guess you're now looking for similar situations for that particular scenario. Is that kind of how you work it out?
So do you mean looking for similar situations in models or in real life?
Well, as in the data in real life. So you said that, you get snapshots of the nurseries, and then you get snapshots, all the way through this life cycle. And, you have to be able to find this scenario where you've got these, stars starting to merge at different stages.
Yeah, that would be very, very difficult. So we know of multiple systems, so that's not something that we kind of pulled out of a hat. That especially massive stars tend to prefer having several friends, so that's not too hard. But then knowing the lifetime is more of a crunching the physics. That's the bigger thing. As we get more gravitational wave events, we'll also get better rates, so we'll get a better idea. But yeah, there's loads to do when it comes to the its mechanics. You need to create different systems with different parameters and put it all because there's several mechanisms that occur when you have more than two stars orbiting each other. You've got special kinds of instabilities that can occur that can help accelerate this process. So that's quite interesting, where if you don't put enough physics, it doesn't work, but when you put more complex stuff, it actually helps. Sometimes you're not making your life harder by making it more complex. You're just getting closer to the answer. But Yeah, I know a few people who work on that kind of stuff. For me, it's magic. I
Yeah.
love it. Like, I have a friend who worked on something like that for just some other system that has nothing to do with these things, but still multiple systems. And so it was a triple system. And at some point in the evolution, the orbits become chaotic, and so they do crazy things.
Wow.
Like the picture of that orbit is insane. Like, it looks like looping. Yeah, like, and then
That's nuts.
and then something merges, and then it calms down again, and it's like, okay. But for a few thousand years, the system is like all over the place.
Oh my goodness.
But the thing is, because those phases are so short, that
Yeah.
we can see, then it's not something that's easily observable. Because obviously,
Mm.
if they last the blink of an eye in
Yeah.
the lifetime of the universe, then you're not likely to be able to observe it very easily and um, capture those things.
Yeah. Yeah. It's again all about scale.
Mm-hmm.
So,
Exactly.
yeah, with I guess, the amount of data that we still have from, 25 years ago, is do people often trawl all of the old data to see whether they can find these things that they're looking for that they can't find now? Is that a thing?
Yeah, I mean, it's that's quite interesting. So working with archival data is definitely a thing. Um, I mean, most of the data that I work with is not stuff that is fresh out of the telescope. It's stuff that's already been taken by people. There's a guy who made his entire career because he had a brilliant idea. He was like, "Oh, well, these supernovae have exploded in these galaxies, but the Hubble Space Telescope took pictures of these galaxies a little while ago. Let's see if we can find the star that
That's
exploded as a
specific, yeah.
supernova. If it's gone, then it's the progenitor." And he found a whole bunch, and he got a medal for it. Actually, like, he's one of the biggest guy in the field. He leads
Yeah.
the team. He's not anymore, but he helped develop the team of Engrave and stuff like that. And um, yeah, it was just looking at archival data and
Yeah.
doing that in a clever way, and it taught us a lot about the kind of stars that lead to supernovae because we could actually see them. You know.
Yes. And actually get all the data to get a bit more information about, how that tracks and how it kind of leads towards that event. That's very neat.
Exactly, because then you can compare that to the models and see what it looks like. So it's really awesome.
Yeah. So, with your area of focus, how did you kind of, from all the things you could possibly choose from, what led you down the path to supernova and kilonova?
I just like things that go boom.
Straightforward to the point.
I
Excellent.
kind of I like things that go boom. I like understanding how things work. So I think stellar evolution is definitely something that makes sense. Um, More sense than the spectropolarimetry because that was very niche. It was a very niche thing. The thing I'm doing now has much more scope, which is kind of overwhelming. Of like, oh, there's so many things to do, but at the same time, it kind of suits me a little better. I like things that go boom, so that's and it's just such an exciting new field, Kilonovae. And obviously, I was on the outskirts of that for a long time, but hopefully, I'll be able to contribute to it and get more into it as we get more data and really be an active participant in this field. But yeah, just massive stars are just my favorite stars. They do
Yeah.
crazy things. They do crazy things. And I keep getting distracted. I keep getting distracted. I'm supposed to work on Kilonovae and their environment, and that's it. 80% of what I've done in my postdoc has not been that. But partially because the thing was not working, now it's working, so it's going to be better. It's going to be more focused, I promise. But also my boss comes from supernovae and progenitors, so we also got distracted by other things. Like, we collaborated on a paper with a bunch of other people on the progenitor of or the environment of a supernova, a weird supernova. I'm trying to, hopefully it'll get published, but I just submitted a paper on looking at evolutionary pathways for superluminous supernovae. So it's just all of these things that do crazy stuff kind of get my attention a little too easily, I have to say.
Well, how can you possibly not with all the things that are happening? There's just too much.
I know. Shiny thing, shiny thing.
Oh yeah, yeah. Being able to work on all of these things and able to switch your focus from time to time. That's great. Like there's so much to learn, so much to do, so much to see. It's yeah,
Yeah.
definitely. That's very cool. So you put up these videos on Twitter. They're very cool, very interesting. But what got you into doing that? Why did you start doing the outreach?
Oh, I've always loved outreach. It makes me feel useful in a way that science sometimes does not. Science is a very selfish endeavor, like for myself and for my immediate community. But realistically, we're not curing cancer. Um, my very niche interests in science are not any use to anyone in real life. But I can share my knowledge of space and entertain and inspire other people with that. Um, and I've always loved doing that because I'm just really passionate about space, and sharing that
Yes.
energy with other people makes me feel happy. Tonight I'm talking to a bunch of 11-year-olds about space and
Ooh,
stuff, and I can't wait because
fun.
it's gonna be fun.
Yeah.
So I just really love that, and half of my videos on the internet, because I wish I had more time to make proper videos. So half of them are kind of just in the moment, like someone said something really stupid for clicks on the internet. No, absolutely not. This is not how anything works, and let me tell you why. So there is a lot of that, but I try to make it informative and interesting.
Yeah.
And
And that's a good thing. I mean, when you talk about the way that, your area of science doesn't really help in the real world, it doesn't, but it helps in the way that, it allows us to understand more about where we are in this space. And, it's a different type of help.
absolutely. I didn't mean to say it has no value. I just meant to say it has no practical. There's no practical
Application
needs.
to,
There's no practical
yeah,
needs. It's not gonna put food on your table. It's not a practical skill that's gonna help you build your IKEA
yeah.
furniture. You know, it's not something tangible. It's still valuable. It's part
Yeah.
of what makes us human, to seek understanding of things that are way beyond us. And I think it's still
Yes.
important. But I see this as part of it's more. I see this more as entertainment than education. So I try to
Yeah.
educate in everything I do, but I am not lecturing people. This is an exam at the end. It's okay if we simplify. It's okay if they don't understand all of it, so long
Yeah.
as they feel inspired and lifted by what I say. That's kind of all
Yes.
I seek. And that's what I love doing. Actually, that's something I will advertise. It's not I don't get paid for any of it, but on my website there's all my contacts and my emails and my Twitter and everything. And I do things online via Zoom to like schools or astronomical societies or events like conferences or whatever. I'm a public speaker, and I will speak at your event if you let me know, and we can find a date. So I don't charge for educational purposes. So just if you're interested in my work and in what I have to say, then just let me know, because you can just book me. I'm very happy to spend some time talking about these things. That's something I do in my off time because I'm passionate about it.
Exactly. Yeah. So, yeah, definitely. It's not about it not being important because, life, the universe, and everything is about, who we are, what we do, why we're here. And, it's such a literally nebulous topic for most people because we don't really see much of what it involves outside of popular culture.
Yeah, yeah. It's very interesting, and those numbers are so confusing and mind-boggling. Like, it's very
Yeah.
interesting because we have people going too far the other way. So there's a guy corrected on TikTok recently. I was like, oh, if Beetlejuice goes supernova, we won't have nights for 3 weeks because it'll be so bright. And it's like, no. If a supernova exploded close enough to Earth that we would have no nights for 3 weeks, we would have other problems to worry about. But yeah, no, it was crazy because like that's absolutely not accurate at all. But obviously, because the numbers are so crazy in general, it's hard to
Yeah.
know what is fact and what is fiction unless
Yes.
you actually run the numbers. You can't know. Absolutely. And some people are like, oh, but it's so far away that maybe it has already happened. It's not that far away. It's 600 light years away. 600 years is nothing in the life of a star, but people don't, people, oh, it's just really far away, so it's dead already, which is, the concept scale, because they don't match on either side.
Yeah.
If you're not used to these numbers, your brain can't put them together. And it's
Yeah, it's
not
just this weird blur between now and then,
exactly. It's
and
like
it's yeah.
it's really far away and really big, and it's and they just parrot something they've heard before that. Oh, the stars you see are already dead because they're so far away, which is a by the way, that's a lie. If you've heard that before, in fact, and you believe it, it's absolutely not accurate. The stars that we see in the sky, they're really bright and very close. That's why we can see them with our eyes. And they're at most like a few thousand light years away. So they're absolutely not dead at all. Like you can wish upon the stars and you'll find. Some of the stars that you see with telescopes dedicated as like professional telescopes, that are so far away that they are like 10 billion light years away. Yeah, those are break them. But these stars are they're not just in the Milky Way, they're in the solar neighborhood. Like, it's next door, so we're fine.
But yeah, it's bad enough that we've got, fake news about all the stuff that happens, terrestrially, and then now we have to deal with space fake news.
I
Goodness.
know, it's like as a science communicator, because like these people, they only do it for clout, they do it for clicks, but they contribute to people losing faith in science because they see all of these science news that are bullshit, and then they turn out to be bullshit.
Yeah.
And they're like, well, scientists don't know. It's like scientists freaking know. It's just that it's not scientists telling you that shit. It's just some random guy who didn't do his research on the internet. And
Citation, please.
yeah, exactly. It didn't happen. And it's very frustrating, but because and I just don't understand because honestly, the truth is often so much more interesting than the lie, but they have they're just better marketers. They have the clickbait
Yes.
recipe, and they use
Yep.
that for clicks without any regard for the consequences or what that means for science, because this is not their business, and it's very frustrating.
Yeah, it is. Yeah, but that's why the stuff that you're doing is really great because, you go there, you call them out on it, and then you add a little bit more information, say, this is the thing, this is how it works, this is actually what happens, and that's even more interesting and much better than what you just heard.
Yeah, I'm getting the sense that quite a few people are getting into that sort of debunking
Yeah.
content, that's debunking misinformation. I think people are starting to get sick of it. So I'm quite hopeful that we've kind of gotten to a peak of misinformation where it kind of got out of hand without us noticing, but we're talking about this more and more and more, and eventually people will just be so sick of it that it hopefully eventually it will kind of self-regulate itself, where it's just not
Yeah.
going to work anymore, and it's not going to be advantageous to for-profit businesses to use those techniques that are pretty dishonest, to be honest.
They are.
We'll see what happens.
Yeah, well, one can hope.
I'm hopeful. I'm trying to be hopeful.
Yes, definitely. So let's get into some of those other questions that are completely unrelated. So, what hobby or interest do you have that's most unrelated to your field of work?
Right, so I do roller derby, which has nothing to do with science.
Fun! Yeah.
It's all physical. So roller derby is a sport that is played on roller skates, where you have two teams going against each other. 5 people are on track of both teams. So 5 versus 5 on track at any given time. And one of the people in each team is tasked to score as many points as possible. And the way you score points is by lapping the people from the other team.
Yep.
And the way you prevent the other person from lapping you is by hitting them and getting in their way. So it's a full contact sport on wheelie shoes.
The call was disconnected. Resuming.
Roller derby, contact sport,
Yes.
lots of fun, violent.
Yes. It's not violent. It's fully consensual. It's really fun. I love it. And we wear proper pads and all that, and we nearly don't get hurt. Breaks happen occasionally, but not to me so far.
That's cool.
Um,
That's all right. So, what position is yours?
so I played both jamming and blocking. So jamming is the person who scored the points, and blocking is the person who prevents them. Um,
That's cool.
uh, in the last season, which was my first competitive season, but obviously COVID we didn't do much. And I'll be doing more jamming, I think, this season. Kind of depending
Nice.
on what the team does, because I'm not super hung up on what position I play. So if people prefer things, I'll be like, well, I'll do whatever. Like the next game, I'm not even going to be on track because we've got quite a few people that are willing to play. So I'm happy to like be one of the referees. And so I'll be in the middle of the track. You're still on skates and like going with them, but like checking their positions and making and counting the points. So that's the job I'll be doing at the end of March, proper game. So yeah, there's
Nice.
lots to be done on skates. So that's really fun. I love it.
That's awesome. That's cool. So, is that, yeah, is roller derby like pretty popular in Auckland?
It's okay. I mean, we've got two teams in Auckland, but Auckland is a big city of 1.5 million people. Um, it's not too bad, but roller derby in general is pretty niche as a
It is.
but it's surprising how such a niche sport wherever you go there's a team like
Yeah.
there's 16 girls who like just found a gym that will let them use their basketball court like on a Friday afternoon or something like that, and then they're training. So it's amazing. I love it. I love it.
That's awesome. That's brilliant. So, you've just been doing that for, was it, did you say 1 year or?
So I've been in competition season for
Ah,
1 year. So I started in 2018, July 2018. Uh,
cool.
so it's been nearly 3 years that I've been
Nice.
practicing the sport, but it takes a little while to be able to actually play it because
Yeah.
it's a full contact sport on skates. You're not allowed to actually play the game before you've demonstrated your ability to play it safely, for
Yes.
your safety and others, really. So you've got to, be good enough on your skates and understand the rules sufficiently to understand where you're allowed to hit, where you're not allowed to hit, because it's not just a matter of rules, it's a matter of safety. So for example, you're not allowed to hit the back, like the spine is a no,
Yep.
you can't hit with your fists. Uh, so yeah,
Yeah, makes sense.
yeah, it all makes sense in the end.
It's cool. Yeah. So, they've got local teams in Perth. I haven't had a chance
Nice.
to go check them out, but it's been, yeah, I get the impression it's been around for almost 10 years. It's very cool.
Yeah,
Well,
yeah.
probably been longer than that, but it's great.
Yeah, I mean the sport started I think it was very popular in the 70s in America or something like that, but it was completely different. It wasn't really a sport, it was more like wrestling.
Yeah.
But now it's a proper sport with proper rules. So, like we have kept something from that era though. We have derby names. So you pick a name when you're on track, you're not called by
Yep.
your last name or anything like that.
That's cool.
Which is
What's
really
yours?
fun. I'm Dr. Nova.
Dr. Nova. That's a good
My
one.
name
I
is
love it.
it's so weird. It used to be Supernova, but it immediately got shortened to Nova, which technically isn't the same astronomical object, but I wasn't going to put
No.
it like, even though like no one gives it
Actually.
like Nova. It's two syllables. That's as much as we can manage when we're on track and yelling your name to get your attention. Nova it is. And then when I got my PhD, my whole team in Sheffield was like, Dr. Nova, Dr. Nova, and they kept calling me that. So that's my official name. But when I'm on track, people just call me Nova. And
That's cool.
so, yeah, so it's very weird because, like, when you're in the team, you call people by their derby name, and sometimes you don't know really their real name. So
Yes.
when we have league meetings and I have to do attendance because I'm the secretary of the league, it's like, who the fuck is like Pigeon on the list? Oh, Emma, great.
It's funny when you actually get into those circles where you just, you know, the entire community revolves around the nicknames. Because I used to work at an internet provider, and this was, back when there was still dial up. very small. So everyone had their usernames, and it wasn't as though you had first name dot last name like you do with all the fancy corporate stuff. It was whatever you wanted. And it got to the point where one of my coworkers introduced me to his child by my username because he couldn't remember off the top of my head what my actual name was.
Oh my god.
Yeah,
Yeah.
it happens.
I mean, it happens all the time for us. Like,
Yeah, it's cool. Okay. And which childhood book holds the strongest memories for you?
I don't know. I wasn't that much of a reader.
Ooh.
I know. I'm of the generation that should say Harry Potter, but I got bored after the second book, so I'm going to upset a lot of people. Sorry, I didn't really do.
Oh,
Um, so I didn't have really a favorite book that was like fiction,
yeah.
but I remember very fondly um, one of the first books I got about astronomy, which is about the
Ooh.
planets, and it had all. I mean, it was a series of books. It was still at the time the 9 planets, so there was a book
Yep.
per planet, and it had a like squishy cover because it was for kids, like for like
Ah.
6-year-olds, and it was great. And like that's one of the things that sparked my interest in astronomy and in science, and I still remember that to this day because it was such a lovely little collection, um, and
Ah.
it was so good. I love that.
Um, yeah. Well, a lot of the people I've spoken to, the books that they loved as a child tended to be related to what they ended up pursuing later on in some way. It's like,
Yeah,
yeah, this is the thing that, that really intrigues me. This is the thing that I'm now passionate about. It's great. Like you just
yeah,
see this little seeds being planted.
yeah, definitely.
Yeah. Okay. And last one, what advice would you give someone who wants to do what you do? And what advice should they ignore?
I have so so many pieces of advice. Which one should I pick? Um, Learn to code and learn early is what I would say. And also, you're not stupid. Science is just hard. That's something I keep telling
Yeah.
students consistently, and I have to keep telling myself. You're not dumb. It's just that science is hard. When it starts getting difficult is when it starts getting good. So,
Yes.
um, and what advice should they ignore? Well, if you're going to be in uni and you've got all of the people being like, oh, just come to the library, we'll just work all through the night for the exam tomorrow. Don't do that. Don't pull all that. That's a stupid thing to do. I mean, I never did it, and the people who kind of forced me into that, I hated them with a passion. Um, like, writers just revise the day before and then have a good night's sleep. Like, your anxiety will thank you. Yeah, don't listen. Just don't listen to these people.
Yep. Definitely.
They're no good.
No. And yeah, it's a false economy.
It just doesn't. Uni was amazing. Like the people who talk the most are the ones that have the least to offer in my experience. There were two kinds of big talker. The ones that are like, oh, I never do anything, blah blah blah, blah because they prided themselves into being able to still get through without putting any ounce of effort, which is like weird flex, but okay. Do you? And the people who had been worked the whole time, which is like, okay, you have no life. Congratulations. This is not what's not clicking.
Yeah, exactly.
So yeah, people that gloat about either doing more work than they should or not enough work, it's just they're not worth your energy whatsoever.
Yes,
Usually they're lying
definitely true.
about it either way. To be fair, like so.
It's good. Good advice. Because yeah, when you're when you're at uni, there's a lot of rubbish, there's a lot of BS that happens.
And everyone's so young and impressionable, and it's peer pressure, but like in a very subtle sense, like because you're comparing
Yeah.
yourself to your peers, and you need the reassurance of like, am I doing what I'm supposed to do?
Yes.
Because you don't know yourself in work and in a learning, and I mean you've been in school for so long, but you've not really
It's a
been
different learning environment
different learning
when you go.
environments, and
Yeah.
like some people have been challenged by that point, but for a lot of people like myself included, you haven't really been challenged by school. Let's be honest, like you spend most of the time
Yeah.
fucking around and and you still got there. Which makes sense, because school isn't just about learning, it's about socializing and making human beings that are going to be functional in the workplace. It doesn't always
Yes.
work, but that's part of the effect. But there is so much more to learn about yourself and how you work and how you learn when you're in uni that it is confusing. But yeah, letting yourself be impressed by people that are saying a ton of shit, because they're probably they're probably full of shit, to be honest. Like, if they're
Yes.
being really loud about it, don't pay no mind.
Lesson 1, hone your bullshit detector.
Yes.
Skills to pay the bills.
Yeah, absolutely. Like, this one will save you time in the workplace, 100%. That's probably the thing that will be the most useful out of a degree.
Yes, I think so. Very cool. Okay, so if people would like to learn more about what you do and, more about you, where can they go?
So I'm on Twitter and on TikTok when I'm not gone for 2 weeks because of writing papers and stuff, but I'm mostly there. And I answer all the questions at Sidonahi, which is a weird spelling, Sydonahi. It's a weird username from the 2000s. I should probably have changed that handle at some point, but it kind of grew with my platform, and so
Yes.
I'm stuck with it now. It's a remnant of when the internet was in its infancy. I can't get rid of it. The stupid username I got when I was 14, and it's like, we're going to live with it, okay? And there's my website, which is much more sensible because it's my name. It's hfstevance.com. And there's links to my Twitter if you can't type the word. There's my email if you need to contact me, my GitHub. You can find more about my research, and you can find a list of all of the SciComm events that I've participated in and that kind of stuff, to see if there's anything that floats your boat, which there probably will, because at this point I've done everything under the sun. I've done radio interview. I haven't done is TV interview. That's everything. So
one day. Cool. Okay. So thank you so much, Heloise. This
Thank you so much
amazing
for having
talking to
me.
you about all this.
It was so
Yeah, this
fun.
is so great. Yeah. So learning so much. Gosh, I crash coursed last week about stars, and it's like, oh my god, so much stuff. And at one point it's like, nope, shutting down right now. Too much math. But so interesting. Same. That's great.
Me at 3 p.m.
so
every day.
Well, so as you said, science is hard. It's a thing, and that's very cool. It's what makes it good. It's what makes it interesting.
Exactly. It's the problem solving. Otherwise, it wouldn't be fun.
Exactly. Cool. All right. Well, thank you again. It has been absolutely awesome. Can't wait to see all the other stuff that you're working on. And yeah, very cool. And thank you so much, and have a great evening.
Yeah, you too. Have a great whatever time it is for you.
Morning.
Morning.
Just barely.
Have a good afternoon. Have a great lunch.
Okay.
Bye.
Yes. Bye. When you think about the vastness of space, things that we don't know but could learn about is literally astronomical. It's such a relatively young field, and what we know just barely scratches the surface of what there is to find. And with further technological advancements, we're going to keep being able to discover new things and refine findings even from decades-old data. If you're looking for a pursuit that's about life, the universe and everything, this might well be the place to start. To learn more about Heloise and what we discuss on this show, or to connect with us, please visit the STEAM-powered website at steampoweredshow.com. You can also reach out to Heloise on Twitter, TikTok, and her website, the links of which will be in the show notes. If you enjoyed this conversation, please let me know. Subscribe to this channel, leave a comment below, and share this with your geeky and geek-curious friends. You can also support Steam Powered on Patreon and Ko-fi under Steam Powered Show, the links of which will also be in the show notes. Thanks for watching!